Imagine for a second that someone hands you $1 billion.
Right. A nice casual Tuesday.
Yeah, just
Yeah.
$1 billion in a briefcase.
Yeah.
But it's not to buy a private island or like a sports team. You are handed this money to build the most advanced artificial intelligence architecture in the world.
The holy grail of tech.
Exactly.
Yeah.
So you assemble a team of absolute visionaries, right? You work in total secrecy for years.
Mhm.
And after all that time, all that capital, you have exactly 0 products to show for it.
Nothing the public can actually log in and use.
Right. Nothing.
Yeah.
Meanwhile, you look out the window and your competitors are just launching shiny, mind-blowing, industry-disrupting tools every single week.
Just relentless.
So the question is, are you a genius who is playing a very long, very brilliant game, or are you just getting left in the dust of the next industrial revolution?
And that scenario, it is the ultimate Silicon Valley nightmare right now. It's that tension between the purity of a grand theory and the brutal, unforgiving reality of the market. And right now, that tension is completely defining the most expensive arms race in human history. To really understand the stakes of this deep dive, we are looking at a landscape that has become heavily polarized around one specific, heavily capitalized phrase.
The buzzword of all buzzwords right now, the world model.
The world model, exactly.
If you've been following the capital flows, you know that Jan LeCun famously left his long-term position at Meta. I mean, he spent over a dozen years shaping their AI division, and he walked away to start AMI Labs.
With over $1 billion in funding.
Right. And as in that opening scenario we just talked about, he is betting everything on theoretical purity. He hasn't shipped a product. He's playing the long game.
But then on the other side of the battlefield, you have figures like Fei-Fei Li at World Labs, alongside the heavyweights at Google DeepMind.
The Shibit crowd.
Right. They aren't waiting for the perfect unified theory of physics to materialize in a white paper. They are shipping usable commercial models right now.
And the divergence in strategy there is just staggering because they are fundamentally disagreeing on what artificial intelligence requires to graduate from pattern recognition to actual cognition.
But, the market has a way of flattening all that nuance.
Yeah.
The venture capital ecosystem has just decided that world model is the magic term that unlocks the treasury, which has led to this really fascinating distortion in the industry.
The distortion is so real. You have AMI Labs, World Labs, DeepMind, and NVIDIA taking entirely different mathematical and architectural approaches. But they're all selling their work under the exact same name.
Yeah, let's look at Fei-Fei Li's company, World Labs. I mean, they have been around for less than 2 years.
Barely any time at all in tech years.
And they launched Marble. Marble is designed to take a text prompt, or just a static picture, and generate a fully interactive 3D environment for commercial use.
So it is essentially an incredibly sophisticated 3D asset generator.
Exactly. But then you contrast that with Google DeepMind's Genie 3.
Which is a whole different beast.
Entirely. Genie 3 doesn't just create a static asset. It generates real-time, navigable 3D worlds entirely from text prompts.
So not just a background for an ad.
No, the computational overhead for Genie 3 is in a different universe compared to asset generation. We're talking about generating coherent environments at 24 frames per second. The physics and lighting have to maintain continuity over generations lasting several minutes.
Wow.
It is basically conjuring playable, interactive game environments on the fly and constantly recalculating the user's perspective.
Okay, so that's 2 versions of a world model. But then you look at NVIDIA's platform, Cosmos.
Right, which is doing neither of those things.
Exactly. Cosmos isn't making 3D assets for ad campaigns, and it's not generating playable video game levels. Cosmos synthesizes training data specifically for autonomous driving and robotics.
It's a totally different application.
Yeah, it simulates how a specific LiDAR sensor would react to, like a specific type of fog rolling across a highway at 60 miles per hour. It's a synthetic physics engine for industrial hardware.
But the sources note it has been downloaded over 2 million times under the exact same banner of being a wind model.
I found an analogy in the source material that perfectly captures the absurdity of this for anyone trying to navigate this space.
Oh, the beverage aisle one. I love
It's
this.
so good.
Yeah.
So imagine you walk into a supermarket and you see an entire aisle with a massive sign that says beverages.
Makes sense so far.
Right. But you walk down the aisle and sitting side by side on the shelf, you have a bottle of Coca-Cola, a bottle of white vinegar, and a giant jug of Dawn dish soap.
Technically, mathematically, they are all liquids.
Exactly. They are all liquids, but you only want to drink one of them, you cook with another, and you clean your car with the third. That is a world model industry right now. The branding is identical, but the utility and the underlying chemistry are entirely different.
And the Ars Technica report we are analyzing today captures this perfectly. They note that world model is becoming a branding term as much as a technical one.
Which happens in tech cycles all the time.
Oh, absolutely. When a specific phrase becomes a prerequisite for securing a Series A funding round, the structural integrity of the term just collapses.
You just slap the label on whatever you're making.
Right. If you are doing 3D asset creation, hey, it's a world model. If you simulate autonomous driving, world model. Advanced video generation, world model.
But the danger of that branding is that it masks this huge philosophical civil war. Whether you are an investor, a developer, or you're just trying to understand where computing is going next, this beverage aisle confusion hides the fact that the industry has split into two heavily armed camps.
Two completely different technological routes to building an AI that actually understands reality.
Right, so let's strip away the marketing labels and look at the actual engines under the hood. The first route is what we can call the generative route. This is the ship it crowd.
The brute force approach.
Yeah, brute force visual prediction. You feed the model massive amounts of video data, hours and hours of how the world looks as time moves forward. And the model's job is to predict the very next frame, pixel by pixel.
So if it sees a video of a baseball flying toward a window, it has to calculate the exact position of the ball in the next millisecond.
The exact spiderweb pattern of the shattering glass.
Right, and the exact refraction of light on every single shard.
The appeal of the generative route is obvious, right?
Yeah.
It's immediate and visceral.
Yeah, it yields these beautiful photorealistic video generations that serve as undeniable proof of progress.
But the architectural mechanism required to achieve that, specifically the reliance on diffusion models, is computationally ruinous.
Every single time the model generates a frame, it isn't just drawing a picture like a human would. It is executing this massive denoising process.
Let's actually break down that denoising mechanism, because predicting pixels sounds simple until you look at the math of latent diffusion.
It's wildly unintuitive.
It really is. The model doesn't just sketch a baseball. It starts with a frame of complete randomized television static, pure Gaussian noise.
And the AI has been trained on a process of disruption.
Right. During training, researchers take a clean image of a baseball, and they systematically add noise to it step by step until it's just static.
And the AI learns how to reverse that specific mathematical degradation. To use a physical analogy, it is like trying to unbake a cake.
Unbake a cake, I like that.
Yeah, imagine you are handed a pile of crumbs and chemical components, and you have to reverse engineer the exact structure of the original cake.
So in inference, when it's actually running, the AI looks at the pure static, consults its prompt in its previous frames, and mathematically subtracts the noise over dozens of iterations to reveal the baseball.
And doing that once for a single high-resolution image requires heavy GPU utilization.
Now imagine doing that 24 times a second, continuously, just to maintain a 30-second video of that baseball shattering a window.
The computing power required is just staggering.
The source material highlights a brutal real-world consequence of this exact architecture. OpenAI actually killed their Sora video platform this year.
They didn't just pause it.
No, they killed it. The compute cost to run the denoising process for pixel-perfect videos was so astronomical that they had to redirect that processing power just to keep their foundational text models running efficiently.
I mean, if OpenAI, with their almost unlimited resources, is buckling under the compute costs of the generative route, it shows that the architecture has a fundamental scaling flaw.
Which brings us to the alternative, right? The path championed by Yann LeCun and AMI Labs, the GP route.
GP, Joint Embedding Predictive Architecture.
Right, and it is a direct reaction to the computational bankruptcy of pixel prediction.
The fundamental thesis of GP is that rendering pixels is a colossal waste of processing power because the visual noise of the world is largely irrelevant to the physics of the world.
So instead of predicting pixels, GP predicts physical states in a latent space.
Exactly.
But that phrase, predicting states in a latent space, that is the kind of academic jargon that just obscures the genius of the concept for most people.
It sounds like science fiction.
It does. But latent space isn't a physical place. It's a mathematical representation. It's a compressed map of the underlying variables that actually matter.
The source uses a really brilliant example to illustrate this. Think about an antique teacup sitting on a table.
Okay, an antique teacup.
Right, and it has an incredibly intricate painted floral pattern all over it. Tiny blue and red flowers. Now imagine a human hand reaching out to grab it.
If you are using the generative diffusion model we just talked about, that AI is allocating massive matrix multiplications to predict exactly how the shadow from the approaching hand will fall across, like, the third blue petal of the painted flower in the next millisecond.
It is rendering the floral pattern perfectly.
But from a physics standpoint, the floral pattern has absolutely zero impact on the interaction.
Right. The color of the cup doesn't change its mass, its friction coefficient, or its trajectory when it gets bumped.
So the GPU model simply doesn't care about the flowers. It strips away the visual rendering entirely.
In the latent space, that teacup is reduced to an abstract mathematical vector. It just represents a rigid cylinder of a specific mass at a specific coordinate.
And the hand is reduced to an articulated appendage moving at a specific velocity.
So the GPI model calculates, okay, object A is at this coordinate, object B is intersecting that coordinate at this velocity, therefore the state of object A will transition to this new coordinate.
It predicts the physics, not the picture.
Exactly. And the efficiency gains from that abstraction are enormous. By discarding the requirement to denoise and render high-resolution visual textures, the source notes that the GPI architecture is roughly 1.5 to 6 times more efficient to train than generative models.
You are utilizing your GPU clusters to calculate the fundamental laws of motion rather than, rendering the aesthetic dressing of the environment.
But the drawback is severe when it comes to the business of AI.
Oh, massive drawback. Because you cannot put a mathematically pure representation of a latent space on a stage in front of venture capitalists and expect a standing ovation.
Right. If you are a founder trying to secure a billion-dollar valuation to afford your next shipment of NVIDIA chips, a spreadsheet showing efficient physical state prediction doesn't open checkbooks.
It really doesn't. But the 30-second text-to-3D photorealistic generation of Cyberpunk City, that does. The market rewards the tangible in the short term.
Which places the theoretically superior architecture at a massive funding disadvantage.
And LeCun is acutely aware of this dynamic, which is why his rhetoric has been so uncompromising lately. Upon launching AMI Labs, he made the bold claim that scaling up large language models will never achieve artificial general intelligence.
Never. He argues that LLMs are fundamentally autoregressive text prediction engines. They are glorified autocomplete.
Glorified autocomplete?
Yeah, they map the statistical probability of word sequences based on human language patterns, but they possess zero grounded understanding of physical reality.
Like if you prompt an LLM with the scenario, I pushed a heavy glass off a 10-story building onto concrete, it knows to output the word shatters.
But it doesn't output shatters because it understands gravity or terminal velocity, or the tensile strength of glass.
Right, it outputs it because those text tokens just appear near each other in its training data all the time.
LeCun's bet is that you cannot brute force your way to AGI through text statistics. You have to build an architecture like JPA that natively calculates the physical mechanics of the universe.
But the counter-argument from the Ship It camp is grounded in the brutal history of tech adoption. Theoretical correctness is an academic luxury.
Fei-Fei Li's World Labs has marble in the hands of commercial users right now. DeepMind is iterating on Genie 3.
And in the history of Silicon Valley, good enough and widely adopted almost always defeats perfect but still in the lab.
The ecosystem just builds around the tools that are available, flaws and all.
Regardless of whether the generative pixel predictors or the GPA state predictors win this architectural war, both of these engines are slamming into a massive, unprecedented bottleneck right now. And it's not a compute bottleneck.
No, it's a fuel bottleneck.
Yeah. The previous generation of AI, the text-based LLMs, they succeeded because of a massive historical free lunch. The entire internet was this neatly packaged, digitized buffet of training data.
Blogs, digitized books, forums, code repositories.
They just scraped it. All of it.
But world models require a completely different diet. To teach a machine the laws of physics, you need physical perception action data.
And this is where the digital realm fails completely. Text does not contain physics.
You have to extract the data from the physical universe, which requires an entirely different infrastructure.
We are talking about highly specialized, heavily synchronized sensor arrays. It requires multiple angles of high frame rate video, perfectly time-stamped to depth maps.
It requires LiDAR point clouds where lasers are continuously sweeping an environment, timing the photon return rate to build millimeter-accurate 3D topographies of spaces in real time.
And force feedback telemetry. Knowing exactly how many newtons of pressure a robotic servo is applying to an object before it slips.
And the complexity of parameterizing that data into a tensor format that a neural network can actually digest is immense.
The transition from text to physical data represents the end of the scraping era and the beginning of the hardware harvesting era.
Okay.
I want you to think about the sensory reality of picking up a glass of ice water covered in condensation.
Okay.
You instantly know what a wet glass feels like. Your brain seamlessly calculates the micro-friction on your fingertips, the temperature delta, the slight shift in center of mass as the water sloshes inside, and the exact grip strength required to counteract gravity without shattering the glass.
It's completely instinctual for us.
Right. But that sensory experience, that deeply grounded physical intuition, does not exist in the HTML code of Wikipedia. You cannot scrape the friction coefficient of condensation from a blog post.
To acquire that intuition, you have to capture it in the real world. And this introduces what the sources identify as the invisible moat defining the next decade of AI.
The invisible moat.
Yeah, NVIDIA's Cosmos platform didn't just emerge from a software repository. NVIDIA spent years building entrenched partnerships with autonomous driving companies, advanced robotics labs, and heavy industrial manufacturing facilities.
They systematically deployed hardware to accumulate 20 million hours of this multimodal sensor data.
20 million hours, and the business implications of this are staggering.
A brilliant team of engineers at a brand new startup might be able to reverse engineer a competitor's neural network architecture in a few months, right? Algorithms can be copied.
But you cannot magically conjure 20 million hours of synchronized LiDAR, force feedback, and robotic trajectory logs.
You cannot speedrun the physical passage of time required to harvest that data. It is an unbreachable defensive moat built on real-world hardware deployment.
It really explains the sudden, aggressive pivot by major tech conglomerates into physical hardware over the last couple of years.
The push to put sensors on appliances, the massive investments in warehouse robotics and autonomous logistics, it is not merely about selling a smarter vacuum or a self-driving truck.
The hardware is a Trojan horse for data harvesting. They are strip mining physical reality to feed the training loops of these world models.
Which forces us to confront a terrifying vulnerability. If these multi-billion-dollar world models are learning how to operate in the physical world solely by mapping statistical patterns across this sensor data, what happens when the pattern breaks?
That is the multi-billion-dollar question.
Right. What happens when a model that is actively steering a vehicle or operating a surgical arm encounters a scenario it hasn't mapped in its 20 million hours of training?
The sources provide a highly detailed, deeply concerning answer to that question. They specifically point to a 2026 paper designated Archive 2604.01346.
Okay.
The researchers systematically analyze the security risks of world models, and they prove mathematically that these systems are vastly more vulnerable to adversarial attacks than LLMs.
Vastly more vulnerable.
Yes, and the vulnerability stems entirely from the deployment environment. World models run in closed-loop decision systems.
Let's define the mechanics of a closed-loop system, because it's the engine of the failure here. An LLM operates in an open loop. You type a prompt, it generates text, the transaction ends.
It's isolated.
Exactly. A world model in a robotics application is a continuous, unbroken chain of consequence. The model reads the sensor data, calculates the physical state, executes a motor action, reads the new sensor data generated by its own action, and loops again dozens of times a second.
And the paper specifically targeted an architecture known as a GRU-based RSSM.
Right.
To appreciate the elegance of the attack, we need to unpack how that architecture functions. RSSM stands for Recurrent State Space Model.
And its primary innovation is splitting the model's understanding of the world into two tracks, right?
Exactly. It separates the deterministic states, things it knows with high certainty, like the specific angle of its own robotic arm.
From the stochastic or random states.
Right, like the unpredictable movement of a human walking past.
And the GRU component is a gated recurrent unit. In a closed loop, the AI needs memory. It can't just react to the current frame. It has to remember the velocity of the human from 3 frames ago to predict where they will be in the next frame.
The GRU acts as a memory valve. It uses mathematical gates to decide what historical information is relevant enough to keep in its hidden state and what noise it should discard.
And the researchers exploited this exact mechanism using what they termed a continuous trajectory attack.
They didn't try to blatantly hack the system all at once. Instead, they recognized that in a closed loop, even a microscopic mathematical error in frame 1 will compound.
By frame 50, that tiny error has accumulated into a catastrophic hallucination.
The mechanism of the attack is chilling, honestly. The researchers subtly injected noise into the sensor data, feeding the stochastic track of the RSSM.
It was so subtle that the GRU didn't filter it out.
Right, the model believed it was accurately predicting the environment, but the attackers were slowly hijacking the reward signals.
The internal mathematical gradient the AI uses to confirm it is taking the correct action.
They amplified those reward signals by 2.26 times. The AI became incredibly confident that it was performing its task flawlessly, even as it was physically veering wildly off course.
The most alarming finding in the paper wasn't just that the attack succeeded, it was how resistant the model was to being fixed.
Yeah, the standard defensive protocol for neural networks is adversarial fine-tuning.
Essentially, exposing the model to the attack during training so it learns to recognize and ignore it.
But when applied to the GRU-based RSSM, adversarial fine-tuning only mitigated the continuous trajectory attack by a maximum of 59.5%.
That's practically a coin toss.
The architecture's reliance on closed-loop state prediction makes it inherently susceptible to error accumulation. You can't just patch it out.
We have to pause and absorb the stakes of a 40% failure rate against a known attack vector. We are conditioned to treat AI failures as digital annoyances.
Like a funny hallucination.
All right, if an LLM hallucinates, I get a weird poem or a fake legal citation. It is contained to the screen. But when a world model hallucinates in a closed loop, the consequences are instantly translated into kinetic energy.
A 2-ton autonomous logistics vehicle accelerates into a concrete pylon.
A factory robot swings an articulated steel arm through a space occupied by a human technician. The authors of the paper draw a hard line here. We absolutely cannot treat world models with the same red team content filter mentality we use for chatbots.
These systems require the exact same mathematical rigor, redundancy, and paranoia that aerospace engineers apply to flight control software on commercial airliners.
And that flight control analogy is paramount because it exposes the core illusion of world models, an illusion laid bare by something called the INFIZ-2 benchmark.
The INFIZ-2 benchmark is basically the ultimate reality check for the industry.
It's a test designed to determine if an AI has actually internalized the fundamental laws of physics. The methodology is simple but brilliant. They show the model a series of videos, and interspersed among normal physics are videos containing blatant, impossible violations of natural law.
Like a solid steel block passes straight through a solid glass wall without breaking it.
Or an object drops and falls upward. A ball rolls behind a pillar and simply ceases to exist. It tests object permanence, continuity, gravity.
When human beings take the INFIZ-2 benchmark, even young children, they score near perfect.
A toddler watches a block pass through a wall and immediately looks confused because human cognition possesses an innate, grounded understanding of physical boundaries.
But when researchers subjected the absolute state-of-the-art world models to this benchmark, the models scored close to random chance.
Random chance. After digesting 20 million hours of physical sensor data, the models couldn't definitively recognize that a solid object cannot pass through another solid object.
Because the benchmark proves that these models do not actually understand physics.
At all.
They have not internalized gravity as a fundamental law of the universe. They are merely executing unimaginably complex visual statistical pattern matching.
They have processed millions of frames where a ball hits a wall and bounces. So the statistical probability of a bounce is near 100%. Therefore, they predict a bounce.
But they do not know why the bounce occurs.
The implication for safety is terrifying. When a human operator encounters a bizarre edge case, say black ice on a road that looks like wet asphalt but acts like glass, our performance degrades gracefully.
We realize our mental model is failing. We slow down, we hesitate, we engage caution.
But a world model running on statistical probability does not degrade gracefully, and it does not experience hesitation. When it encounters an edge case that falls outside its training distribution, it doesn't warn the system that it's confused.
No, it jumps instantaneously from executing nominal prediction to catastrophically mathematically wrong. The system just breaks.
Which forces us to step back and evaluate exactly where this technology sits in the broader historical context. The sources draw a compelling parallel here. The industry consensus regarding world models today perfectly mirrors the atmosphere surrounding large language models in 2018.
2018, the primordial era of the GPT architecture.
Exactly. The original Transformer paper had dropped and early text models were emerging.
The entire field could feel the gravity shifting. Everyone knew that scaling these autoregressive models was the correct general vector, but nobody knew the specific formula.
Was the answer more parameters, better quality data, a different attention mechanism?
It was a period defined by massive capital expenditure and immense technical uncertainty.
And the Ars Technica piece perfectly encapsulates this moment for world models, stating, "It's not a scam nor a solved tech. It is an early, expensive, genuinely difficult bet."
And because it is a foundational technology, because it dictates how machines will interact with the physical world, it is inextricably tied to the geopolitical landscape.
The source material outlines the strategic board, specifically analyzing the dynamics between the United States and China. Currently, China lacks the highly visible, heavily funded startups in the world model space, like an AMI Labs or a World Labs.
Tech giants like Alibaba and Baidu possess highly advanced video generation platforms, but they notably avoid leaning into the world model branding hype cycle.
Which is interesting, right? If they have the tech, why not use the buzzword?
Well, the absence of that specific hype is largely driven by severe hardware constraints. The training of these models demands an astronomical volume of raw computing power.
And the U.S. export bans on high-end AI semiconductors, specifically targeting the latest generations of NVIDIA hardware, mean that Chinese research teams face a much tighter compute bottleneck than their American counterparts.
If the generative route requires devastating amounts of compute just to run the denoising process, that route becomes structurally untenable when your chip supply is artificially restricted.
But the source highlights a massive strategic counterbalance. Building a world model is a dual constraint problem. You need the compute, but you also need the data.
And while the U.S. controls the silicon, China possesses an unparalleled advantage in real-world physical perception action data.
Consider the sheer scale of their manufacturing sector, the density of their complex logistics networks, and their aggressive deployment of autonomous driving fleets in major cities.
They are generating an absolute mountain of the exact LiDAR, force feedback, and trajectory data that these models are starving for.
This creates a fascinating divergence in evolutionary paths.
The source posits a critical thesis here. The ultimate victor in the world model race won't necessarily be the entity that publishes the most mathematically elegant paper on latent space physics.
The true value of this technology is unlocked at the application layer.
Exactly. If a Chinese tech conglomerate is restricted from engaging in the brute force compute arms race, but they possess comprehensive sensor logs from thousands of automated factories and delivery networks, they are incentivized to optimize for hyper-specific applications.
They don't need to build a generalized model that can simulate a cyberpunk video game level and a surgical robot simultaneously.
Right, they just need a model that can flawlessly manage a massive automated port facility.
By focusing their limited compute on their overwhelming data advantage within specific industrial silos, they could effectively bypass the theoretical civil war entirely.
The market will adopt a localized model that reliably automates a supply chain over a generalized model that occasionally hallucinates the laws of physics.
The geopolitical constraints might actually force a more pragmatic, application-driven evolution of the technology in that region.
It's a huge strategic shift.
We have mapped an incredibly complex frontier today. We started by cutting through the beverage aisle confusion, where the world model label is haphazardly slapped onto everything from 3D asset generators like Marble to full physics simulators like Cosmos.
We explored the deep architectural divide.
The generative route, spending fortunes on compute to unbake the noise from pixels, versus Yann LeCun's JEPA architecture, stripping away the visual rendering to predict physical states efficiently in a mathematically abstracted latent space.
We identified the invisible data moat, recognizing that the era of scraping text from the internet is over. It's replaced by the arduous, hardware-intensive process of harvesting LiDAR and force feedback from the physical world.
And we analyzed the terrifying vulnerabilities exposed by the 2026 security paper, detailing how the closed-loop nature of GRU-based models makes them highly susceptible to continuous trajectory attacks.
And how the INFIS 2 benchmark proves these systems are just matching statistical patterns rather than understanding the laws of physics.
And finally, we looked at how chip restrictions and data wealth are shaping entirely different geopolitical strategies for the deployment of this technology. It is a brilliant, chaotic, and dangerous moment in computing history.
It really is.
But as we close this deep dive, there is one final, provocative reality I want you to sit with. We spent a lot of time analyzing the data moat. We established that physical, real-world data, the microfriction of a robotic grip, the spatial mapping of a LiDAR pulse, is the new oil.
It is the absolute prerequisite for teaching AI the physics of our universe.
Over the last 2 decades, society unknowingly gave away its digital footprint. We handed over our tweets, our blog posts, our private photographs, and our digitized books entirely for free,
We fed the LLM revolution.
allowing tech conglomerates to build trillion-dollar valuations on the back of our freely surrendered text. We didn't realize the value of the data until the models were already built. So if the most valuable commodity on Earth is no longer text, but spatial, physical, human action data,
Mhm.
how long until the tech industry comes for your physical telemetry?
That's a terrifying thought.
Think about the device sitting in your pocket right now. It contains highly sensitive gyroscopes and accelerometers. It knows exactly how you walk. It maps the cadence of your stride, the force of your footfalls, the exact microscopic angle at which you tilt the screen to counter the glare of the sun.
And your smart home devices.
Yes, think about the smart sensors in your home. The cameras, the motion detectors, the thermostats, they are constantly mapping the thermal and kinetic reality of how a human body moves through a physical environment.
It's all just raw physical data.
Exactly. When the major tech conglomerates realize they need billions of hours of human physical telemetry to ground their world models, they won't ask for it explicitly. They will simply update their privacy policies.
Just another notification on your screen.
Right. When that notification pops up asking for access to your device's advanced motion and spatial telemetry to, improve user experience, will you just click accept terms and conditions out of habit? Will you click accept without realizing that you aren't just agreeing to a software update, but that you're actively surrendering the raw physical data of your existence to train the physics engine of the next trillion-dollar AI?
Something to really think about next time you hit update.
Keep questioning the architecture behind the technology you rely on, and we will catch you next time.